Good morning, or good evening, or good afternoon, or whatever time of the day it is for you. Welcome to the Human Geography online lecture portion for this class. Some of you will be watching this as a part of a hybrid course, and others of you will use this maybe as a replacement for some of the lectures that I do in the regular class. In either case, I would ask you a couple of things. First of all, make sure that you also read the textbook in addition to listening to these lectures. And secondly, as you're going through these and as you listen to the things that I talk about, please take note of things that are interesting to you, things that you're not sure about, and bring those questions with you to class the next time. Because the idea here with a hybrid course is that you do the lecture on your own, and so I'm going to assume that you do that, and that we also have discussion, that we talk about it. So as I go through these lectures, I'm going to leave out some things that I would normally do in the regular class because those are things that facilitate discussion, which we obviously can't have in an online pre-recorded session like this one. Okay, so you should know where to find the online textbook by now. The textbook is free and available to you through a link in the syllabus on D2L. And I'm going to try to do the timing so that each of these is about 20 minutes long or so. Some are going to be shorter and some will be longer. But here we go, okay? So let's talk about the introduction to human geography. I've talked a little bit about this in your class already, most likely, but I want to key in on just a couple of I guess they're not old, dead men from mostly from the Greek Empire. And so, like a lot of disciplines in the Western tradition, we point back to the Greek Empire and the Roman period as this great kind of starting point for Western knowledge. And so, geography is no different. So, our guy is this man whose name I can't necessarily pronounce correctly, Eratosthenes. And notice the time period during which he lived, 276 to 194. Okay, so about 2,200 years ago or so. And he puts together these words, geography, meaning write about the earth. And of course, today geography is much more than writing about the earth. But if you think about that time period, it was really kind of fascinating and incredible to understand even basic things about the earth, the shape of the earth, the size of the earth, what's on the other side of that mountain, etc. So geography still does that, where we are a discipline of discovery, and it's something that I'm going to try to kind of embrace and maybe share with you as this semester goes on. Our discipline has two main divisions, physical geography. Maybe you thought you were going to learn a lot more about rocks and trees and soil types in this class, but you won't. Sometimes it figures into the questions that we ask, but oftentimes it's kind of a side factor because we have these two divisions, and this is a human geography class, not a physical geography class. If we think about this, we study cultural features and their effects on the landscape. We look at the economy and cities and urban form and how communities work together and how they interact with the natural landscape. This is an image from a previous textbook that we used to use. And a physical geographer would look at this image on the right and be most interested in the geologic forms of that rocky coastline, right? And might ask a question about how stable this is. Is this prone to earthquakes or erosion? A human geographer is going to look at this and have a different set of questions. We're going to ask questions like, why did they decide to build there? Do the colors have any meanings? Why are the houses built so close together? Is this linked to a previous time period in which fishing was the main livelihood? And how might that have changed over time? Is this more of a tourist destination now? What is the meaning associated with this place? Okay, so hopefully that makes some sense to you to just kind of give you some context moving forward this semester. Here's another example of a physical landscape that combines with a human-made or a built landscape that is sort of something that's really unique. So physical geographers, again, concentrate on the distribution of the natural features that you can see right on the slide. And human geographers are going to ask a different question about this rock. And so I'll just ask you, can you name where this is? Do you have an idea of where this place might be? In class the next time, I might focus on this and ask you if you had any guesses, but we're going to just keep moving forward for the online portion. So we have these three main questions. This is important for you to know. Where, that's the obvious one, the question that geographers asked most often. Where, why, and finally, what's the significance? 2,000 years ago, the where question was a really hard one, right? Where are we? Where are we in relationship to that sun? That's still a geography question. How long does it take to get from point A to point B? Point B? Are we going to die if we try to do it? Is the world flat? Things like that. So today in the 21st century, we're more focused on the second two parts of this, but we always start with where. Where, why, and what is the significance? I'll just share one example with you of kind of why this matters, not just in terms of directions or our daily lives, but in terms of society and in terms of health. So, geographers have worked a lot on epidemiology, the spread of disease, and understanding how contagion works. And so, there is a disease that maybe some of you have heard of before. It's called Lyme disease. And this is a map produced by the CDC from 2006 of reported cases of Lyme disease. And you'll notice a very obvious geographic pattern here, right? It's just barely crossed the Mississippi River into Minnesota, but you can see the bulk of the cases have been primarily in a region of the United States that I guess we would call New England, but even along the coast. So people in Massachusetts, Vermont, Boston, New York are very familiar with this disease. But moving 10 years into the future, to 2016, we see that the pattern has changed. And so I would ask you to just take a second and kind of observe what those patterns are. And there's a couple of them, right? It's not just in a straight line. But what you find is that, first of all, the reported cases have increased. But secondly, they're moving, right? They're spreading further and further to the south and further inland away from the coast. This is a really serious disease that can cause people to have very significant symptoms. It can really erode a person's quality of life. And there's a lot of controversy surrounding this disease as well. But if you'll notice, it's definitely moving towards us, right? More towards Georgia. You don't see reported cases in 2016 in Georgia hardly at all, but by coincidence, I have an uncle that lives in North Carolina who's been struggling with Lyme disease for a couple of years. And part of the reason that he's had so many troubles is because there is a limited number of doctors that are even familiar with treatment of the disease in North Carolina. And most likely in Georgia, the same is true. I don't have a map from 2018, but it will be interesting to see, and I think it will be quite predictable to see this disease moving further south. So that's just one example of where we use this question of where, and then we look at why and what the significance is as sort of secondary factors, even though they're more important. So geography is a combination, human geography is a combination of multiple disciplines. We borrow from political science and economics and all of those that you can see here, from history, from health sciences, from psychology. And this has a positive effect and a negative effect on our discipline. On the one hand, it's kind of awesome. We can take any question, anything that we're interested in, and you'll see that throughout the semester, I think. Poverty and wealth and food systems and localization and globalization. We can ask almost any question and we can look at it with sort of a lens of geography. On the other hand, it's hard sometimes for geography to distinguish itself from other disciplines because we're always borrowing from everything else. So maps have always been incredibly important. As a matter of fact, the maps that you see on the image to the bottom right here are maps that predate the written language that we have anywhere in the world. And so what that tells us is that humans are instinctively spatial creatures. We kind of understand where we are and how to get from place to place, even places that we can't see. And we've been able to communicate that to each other long before we even had a written language. Now, some would argue that we're losing some of this spatial reasoning. And I think it's not a hard stretch to kind of understand that. If you think about that question right now, can you tell me which direction is west and which direction is east from the place where you're sitting right now? Maybe you can. If you can, that's great. But don't feel bad if you can't. But maybe just think about that a little bit. So again, we have a list here of people that have contributed significantly to geographic thought, understanding space and place. And I've highlighted the three that I'd like you to remember. And so these are in historical order. And so we have Aristotle, and I think most people know who Aristotle was and what he did and the kinds of things he wrote about and thought about, mostly philosophical, right? Logical reasoning and the best way to live life and things like that. But he also wrote and spoke actually, he didn't write, right? He spoke to others about the world around him, right? Gazing into the night sky, wondering what's up there, right? What's our relationship to that? What's humanity's place in the world, right? So we have just sort of the beginnings of geographic thought, but the second guy here that's highlighted, Eratosthenes, again, is the one that we point to as the father of geography. And not just because he put two words together, but he did one specific experiment. At least this is attributed to him. And Eratosthenes lived in, here's an image of him right here, painted a couple hundred years later, if I'm not mistaken. But he was the director of a library in Alexandria, Egypt. You can see it on the map right here. And once upon a time, there's a story in which he went to the well outside of Alexandria and he noticed something at the bottom of that well. He noticed that he could see something that he'd never seen before. Just imagine him visiting this well 2,200 years ago. And he looks to the bottom of the well, and what he can see for the first time is the bottom. He can see the water glistening in the sunlight. Maybe you know where this story is going, but the next day when he came back to the well, he looked down and he couldn't see the bottom of the well. He returned the next day and the next day and the next day, and he could never see the bottom of the well until exactly when? Yeah, 365 days later, after he saw it the first time, he noticed that he could see the direct sunlight hitting the water at the bottom of the well again. And he began to think about what this meant. He began to attempt to measure the angles of the sun using knowledge of trigonometry and geometry. He sent people out to measure the angle of the sun at other places further south from Alexandria. He used things like Pythagorean's theorem, and he calculated that the Earth was in fact round and curved, and that the angle that it faced the sun was changing over time, that it would return to the same position every 365 days. From this, he calculated the circumference of the Earth within accuracy of about 99%, meaning that during the Greek period and into the Roman period, we had scientific evidence clearly written in which the scholarly people of the day pretty much understood that the Earth was round and that it rotated and that the angle changed against the sun over time. Think about how that contradicts with what we've learned, what many of us have learned about what Europeans believed about the Earth 1,400 years later, right? In 1492, before Columbus sailed the ocean blue. Moving past the Greek period and kind of moving after the Roman Empire, right? So this is stuff that you should learn in your history class. We move into what's been known as the medieval period, also known as the Dark Ages, right? This is the first millennium AD, in which maps become less mathematical and more fanciful, like the one that you see on the left, or I'm sorry, on the right here. Okay, basically there's kind of Europe and Asia, which are separated by some water. This is kind of known as a T-map. And these are the kind of maps that start to show up, right? This is kind of a European's view of the world at around 1000. So about 1,000 years ago, there was very little known about the outside world until Marco Polo began to travel to the east, etc. Thankfully, during the same time period, those in the Middle East and North Africa resumed the notion of scientific map making, and they retained that knowledge that had sort of been dropped away by Europeans, because at this time, during the Dark Ages, notions of knowledge change. And again, this is stuff that's straight from your history class, but those that begin to decide what is true and what is not true, the responsibility falls into the hands of two groups of people: political leaders and religious leaders. And so if you were using science and arriving at conclusions that contradicted the church or the state, you could be in big trouble. Moving forward into the age of discovery, or the age of exploration, sorry, not the age of discovery, the age of exploration, Europeans begin to take off, right, and head west across the Atlantic Ocean, and then we have the discovery of the New World, right? So as this is happening, then Europeans are re-embracing science. which results in some amazing maps. So this is a map from 1571 of the world. And by the standards of 1571, if you take a look at this, by most counts, it is pretty darn good. Right now, much was still not known about the world. You can see some images of some kind of enormous creatures. There was still a strong belief at this time that there might be dinosaurs in the world, that woolly mammoths might exist, that there might be gigantic sea creatures and things like that. That was a prevalent belief at the time. But considering the fact that this map maker did not have access to satellite technology or anything else, this is a pretty amazing map. Again, that was from 1571. So the science emerges of cartography, and this is still what's used today. So a map, even today, is a scale model of the real world. I think you already know that, and it serves two purposes. It's a reference tool and a communications tool. I think the first one is pretty obvious, right? It tells us where we need to go and how to get there. The second one needs a little bit of explaining, and I won't linger on this too long, but maps communicate something to us. If you see something on a map, it must be true, right? Take this map from Fox News. I don't even know what the news story was at this time, but this was a story about something that was happening in Iran and Israel and Jordan, and has to do with U.S. security and U.S. military efforts, geopolitical kind of negotiations. Okay, but when I see this map, I immediately know that this map is lying to me. And I have trouble trusting whatever else is coming out of the mouth of the reporter because the map is just dead wrong. I'm not going to tell you why it's wrong, but I challenge you to figure that out. Here's another example of a map that's communicating. This one is more recent. There's been a lot of controversy in the Strait of Hormuz. And so, again, hopefully you can spend some time figuring out where this map is and what's going on in the world. But in essence, there is a lot of controversy and conflict happening between Iran and Western powers like Britain and the United States. But there's also a lot of conflicting reports about where things are happening in that small Strait of Hormuz in between the two countries. Okay, and I'll leave that there for now. To make a map, a cartographer needs to make two decisions about how much of the Earth's surface to depict on a map. And we take this for granted, right? It just shows up on our phone or our tablet or on the GPS unit in our car or whatever. But somebody had to make a decision about how to depict a round surface onto a flat space. And we're just accustomed to that. We see it on a flat space all of the time. And maybe you don't pay much attention to this, but a legitimate map is going to have some type of scale so you can tell, right, what kind of distance you're looking at when you're looking at the map. So Earth is very nearly a sphere. It's not a perfect sphere, but it's pretty close. And so we need a method of transferring a spherical object onto flat space, and this is called a projection. You don't need to memorize the names of these projections necessarily, but just observe how the map that gets portrayed onto flat space looks very different in each one of these methods. So the map of the world that probably was on the wall of your classroom when you were a child is probably not entirely an accurate representation of the world. As a matter of fact, it absolutely is not an accurate representation because depending upon the projection that's used, you get a very different viewpoint. So I applied some different projections to my own younger face so you can kind of get an idea of what I mean. There's distortion that happens, right? For starters, you can't see the back of my head, right? You can only see the front of my face, but then depending upon the distortion, you get a different distance, size, shape, etc. Take this image for a second. This is a map of the world. And what do you notice that's distorted about this map? Or is it accurate? I've kind of already told you that there's distortion that's happening. In essence, what you find is that those elements that are along the equator, so kind of along here, more or less, right, maintain their shape and their size pretty well. But the elements that are outside of the equator, things like up here, get distorted. Right? So the size of Canada and of Russia appear to be much larger than they really are on this map. So I'm sorry, not Denmark, but Greenland, which is this island here, but you knew that already, right, appears to be enormous. It appears to be larger than the entire continent of Africa, which, of course, is patently untrue, nowhere near that large. Canada appears to be much larger. Russia appears to be much larger than it really is. So we can contrast that with there we go. Sorry for the delay there. I'll try to fix that. But we can contrast that with a map like you see to the left, something called the Peters projection or Peters world map, which maintains the area of each country or each landmass as it really is on the Earth's surface. So look what happens to Russia. Look what happens to countries like Norway and Sweden, Canada. They get much smaller, right? The United States gets smaller as well in relationship to other places. But look what happens to the continent of Africa, right? It's absolutely much larger than it appears on most maps like the one you see to the right. Okay, I don't know how to get rid of that drawing, so I'm going to try to do that right now, okay? So every map of the world that's on flat space distorts one or more of these four elements: shape, distance, size, direction. Some of them distort all of them, but a little bit. So we need a way to kind of organize the space of the Earth into meaningful zones. And so geographers have done this, and we have the geographic grid that's used for time zones and for GPS, for navigation, for all sorts of incredibly important things. So I didn't used to teach this because it's kind of like sixth grade stuff, but I'm going to go through it really quickly anyway because I found that students just don't know it, or they've forgotten it, or they didn't learn it the first time. So let's start with the idea of a meridian. A meridian is a line that passes between the North Pole and the South Pole. It's a line that moves up and down, sort of vertically across the Earth. I'll show you an image in just a second here. A meridian is known as also as a line of longitude. The meridian that passes through the Royal Observatory at Greenwich, England, is the prime meridian. On the complete opposite side is the international dateline at 180 degrees longitude. So we can see these on the right side of this screen. The lines of longitude pass through the North Pole and the South Pole, so they all converge at either pole. Parallels, or lines of latitude, on the left side of this image are lines that move across. Right? So you need to remember the difference from those one way or another. The line at 0 degrees latitude is the equator. The line at 90 degrees north is the North Pole, and 90 degrees south is the South Pole. Okay, pretty basic stuff. A line of latitude is also known as a parallel because the lines of latitude never touch one another. They are all parallel to one another. So let's take a look at the map of time zones, and you'll notice that it's not quite as straightforward as you might think. So see if you can find the 0 time marker. Okay, that means that this is sort of where time zones begin. It passes through England and Ireland. It includes Iceland, even though Iceland is quite a ways west from England. And then pass to the south, and you'll notice that the line shifts. So that even as you go directly south from the UK into France and Spain, they're on a time zone that's an hour ahead of that of England. Okay, and these are decisions made by the EU and individual countries for a variety of reasons. Okay, so each time that you move further to the right or to the east, it's an hour ahead, right? An hour earlier. Keep moving until you get to the place where the international dateline appears at 180 degrees, and that's where time shifts. Okay, so as you move across the international dateline from west to east, then something kind of weird happens, right? You go from it being an hour later, an hour later, an hour later, or an hour ahead, to all of a sudden moving into yesterday. Okay? If you move the other direction from Asia, passing backwards or passing to the west across the international dateline, you move from yesterday into tomorrow. It's kind of a strange concept. You have to think about it a little bit. So you might need to spend a little bit of time with that. One of the important points here is the question about why the international dateline appears where it does. Why does it pass and start exactly in England? Is there a scientific reason for that? The answer is no. There's not a scientific reason why it begins there, right? We could do the same thing. We could start time or the time zones anywhere. We could start them in Turkey or in Russia or in the United States. The reason that they start in Greenwich, England is because of the British Empire. So the British Empire was the entity that sort of came up with this idea of time zones and spread them across the whole planet for obvious reasons. When you have an empire in which the sun never sets, where you have entities and areas of control on all corners of the planet, you need a sensible kind of a time system so that when people communicate with each other about things that are being shipped here, there, that there can be a mutual understanding of what that time is. There was a time in which each just local place had its own system of time, and that was fine. So this is kind of reminiscent of the beginning of globalization. One of the most important tools that geographers have today is not just static paper maps, obviously, but digital maps. Underlying most digital maps is something called a geographic information system, which I'll talk more about in just a second. It's the ability to overlay data on top of each other in map form. And one of the most powerful data gathering tools is remote sensing. So you can see the definition. I'm not going to read it right there, but you can see some images on this slide of remote sensing data that was captured between 1999 and 2004, and that shows the change in the flow of a river. This is incredibly important for environmental science, for insurance companies, for government agencies to determine where damage has occurred after a natural disaster. Insurance companies are interested to know where the flood zones are for a particular water system, etc. This is the one that most of you are most familiar with. A GPS, or a global positioning system, is dependent upon a system of about 24 U.S. government satellites that are in orbit around the Earth and are used to determine the precise location of any place on the planet. So there is this question, why did GPS become so reliable only in the 21st century? So in 1999, if you were to get your hands on a GPS, which you could find one at Radio Shack or something like that. If you took it out and attempted to figure out your location, it would work, but only moderately so. It couldn't pinpoint your location exactly. It might be off by 100 meters or sometimes 300 meters. You just didn't know. So obviously we couldn't use this technology for self-driving cars or for delivery systems or anything meaningful. In 2000, however, this all changed, and all of a sudden, GPS systems began to be able to pinpoint a location with massive precision. So my question to you is this: what changed? Why did they become so reliable so quickly? The satellites didn't change. The GPS receiver didn't change. There was something else that changed. And here's the answer. So the satellites in the U.S. context were placed in orbit specifically for military use, right? To spy on those evil Russians or those evil Iranians or those evil Canadians or whoever, right? And in 2000, President Bill Clinton decided that it was time to open up the signal, to descramble the signal so that private sector companies could use that precise location for all kinds of things. And I remember when this happened because President Clinton said that this is going to be worth $1 billion to the American economy. And I thought, nonsense. There's no way that opening up the GPS signal will ever be worth $1 billion. And I was wrong. In 2018, it was about a $20 billion industry. And so, as we know, GPS is used for everything from tracking your packages to search and rescue missions, for military reasons. Police officers use it, tracking devices to track children in some cases, right? Snapchat uses it, etc. So this is a case where the military use kind of outlived its usefulness, and now the private sector is able to use it because of the decision made in 2000. In the 21st century, we have this kind of new problem, as you can see from the image on the right. This is an image of private sector satellites that are kind of roaming around the Earth, and we're moving into a territory now in which we have a real clutter problem because it's become so easy to put a satellite into space. So private companies do it. In some cases, private individuals have attempted to do it. So this is kind of a new problem for the 21st century. Going back to that term, Geographic Information System, or GIS, you should know this term, is a system that captures, stores, queries, analyzes, and displays geographic data used to display or create digital maps. This is a lot more than just digitizing a map and displaying it on a computer screen. There's a set of analytical tools that goes along with this. So by layering data on top of each other spatially, we can answer all kinds of questions that we really couldn't answer before. Even 20 years ago, these would have been really, really hard questions to answer. Think about how this affects things like real estate. If you're in the market for a home and you have specific criteria, you need to be within a certain school district and within 5 minutes of an interstate, let's say. You want to be in a place that has access to parks. Right? We can answer all of those questions very quickly, and maybe some of you have used websites like Zillow before to do such queries. This is only made possible because of geographic information systems. So I'm going to go ahead and stop this segment right here. I don't know what my timing is like.